Joe, can you hear us?
Yes, I can. Can you hear me?
Yes, great.
Good, good.
So no work study yet?
Not yet. We're still interviewing, but we're having trouble finding the student. We just have a class conflict.
Yeah.
How are you doing, Chloe?
I'm okay. I wanted to get this test back, but you know what? Might as well get it over with.
See, there were questions that I felt really, really good on. Like, the first couple questions were pretty easy, and then I got my confidence, and I was like, yes, I'm going to do really good on this. And then, halfway through the test, I got these questions, and I was like, I forgot what to do for this.
Yeah.
And then for that graph that had so many different lines, what did yours look like?
No, I put like 6 different lines. And Brittany said she did like a graph for each, not Brittany, Sydney said she did a graph for each one. I was like, why didn't I do that?
I don't think that was what you were supposed to do.
Well,
I think it's supposed to be one graph. But that was the instructions.
Yeah.
It's got one system of an XY axis. There are just multiple lines.
Yeah.
See, where I did, mine looks like, it looks like it goes like up, and then it has two of the little going down parts. I think I missed one though, like,
Oh, I know.
I was at the end when we were running out of time, I was like, you know what, I just gotta push something down, so I didn't really read all of them to make sure they fit, but that was stressful.
Mm-hmm.
Well, I have your tests.
I feel like I did do good on the proofs though.
Wait,
But I don't know. I guess I'm supposed to hand them back now? I don't know.
Wait, he already graded them? Wow,
Most
he's
people
efficient.
are on top of things. So nice.
He's
That's
efficient,
true.
I will give him
That's
that.
true. I feel like I did do well on the proofs though. Like, even on the infinity proof, I might not have understood what I was writing down, but I feel like it's right.
We need a box of tissues in here.
My allergies are so terrible this week.
Okay, I'm gonna fix the camera right
Do
quick.
you know what that means? The season is changing and it's almost fall.
Which means it's gonna get cold. Like, my throat's actually sore from sneezing so much that I'm like pumping down cough drops. I'm really worried right now because I don't think I had any homework last night, but I feel like that's completely unheard of, and I probably had something due.
What? No homework? What is
That's
this?
what I'm thinking. Like, something has to be wrong.
I don't know. I could see it. Well, we had no homework for this class because we had a test. And then, what other classes do you have?
I had chemistry. I don't think I had homework. Well, I mean, if I did, the class is until Thursday, so I'm still good.
Nice.
And then Spanish, everything's on Friday.
Yeah.
Are you taking Spanish now? Like,
No, I'm not. Not this semester. I was going to take Arabic my senior year, but then I was talking to Miss Johnson. They're going over how you have to have 3 foreign languages, and they only offer 1. Or maybe it's 2. I don't know what it is. So it's like, really? Go with it.
yeah. At the international fair stuff, I got to see the guy who does all the Arab culture stuff.
Mm-hmm.
That was really, he seemed really nice. The international fair was amazing. There was food everywhere.
Nice.
Where was it?
The international fair last year. Weren't you there?
Oh, International Night. Yeah. Yeah, I was there with all my kids.
Yeah.
They loved the food truck that was outside with the big crepes.
I didn't know there was a food truck outside.
There were two. But they had these like crepes and they were like this big.
Oh, nice.
And one of them was like peanut butter and banana or
Oh wow.
no, banana and Nutella.
Oh, that's good.
man.
It was
Why
really
did I go to
good.
the food truck?
It was really good.
Your kids are so adorable, Miss Claire.
Well, thanks. I like to think so.
How old are they?
They are 7, 8, and almost 11 this weekend.
Oh.
The 11-year-old's almost as old as my little sister, my oldest sister.
Don't tell me that.
Well, you might be the same age as my dad, probably.
Probably.
Which, he's much younger than you think.
Still wrapping my head around that. He's been 9 for almost a year, and it's still weird.
But I don't like it. My sister's in double digits, and I was 8 when she was born.
Don't do it. Don't say such things.
And within the next 7 months.
I'm guessing he wants me to pass these out. That's what he sent them to me. You ready?
What's really sad is that my brother being 10 in a few months isn't gonna be the weirdest thing. It's that my little cousin, who is 10 years younger than me, the other day, for some reason, I was like, I don't know, I was just laying down, I was thinking about stuff. And for some reason, I came to the conclusion that when my youngest cousin and my brother start to learn to drive, I'm old enough to be their supervising driver,
Oh
and
my
I don't think I can handle that.
How many? You're 5 years
I
older
would
than
be
me?
too.
I'm 7 years older than my brother and 10 years older than my cousin.
Wow.
Yeah.
You're gonna be in your 20s when they start driving.
I know.
See, it hit me the other day when we were talking about ages, and she's 13, and she's like, yeah, but I'm basically 15 if you round up. And I was like, oh my gosh, I'm 20 if I round up. That's not fair. I don't know what life is like not being a teenager.
It's not as much fun. Actually, college is pretty
Is he
fun.
great on a curve?
I'm excited about college, though.
College is fun.
I got the
I
tour
don't
of
want to look.
Tuesday.
No, I'm not gonna look.
You can do it, Claudia.
No, I can't. I can't do this.
Miss Claire, so did you study in Australia? How long were you there?
I was there for a full semester, so roughly 4 months, 5 months, 4
Were
months.
you able to take classes for your major while you were there, or was it just kind of cultural stuff?
I took one. I only took 3 classes. One was for actually it was for my minor. It's like a business class,
Oh,
but I shouldn't have.
okay.
I would suggest not.
Okay. I was looking into study abroad programs, but I really don't want it setting me back getting my
Well,
degree.
you'll have so many credits though when you transfer that it. I took classes over the summer so that it wouldn't set me back.
Because engineering is still, even with the 2 years here, it's gonna take me 5 years to get an engineering degree, which is really. But it will still be 5 because the amount of classes I can cancel out are pretty. Or
That's what Cat was talking to me about. He's just like, you could just double me.
Are you applying to state?
I want a double major. But the good news is that both my majors have similar classes.
He did write his name on every page though.
Even the backside.
Let's see what my final grade was. 86.
I don't care what the overall.
A 79. I got a 79.
Oh crap, I missed
Why is
that.
that?
I did it.
I missed that.
I spent so much time on that graph. I got
Clear, I
2
don't
points.
know. You can throw it away. I'm not.
Okay, what did you get for number 9 for the given part?
Oh,
didn't know what I was doing. Like, I knew what I was doing in
I
the
got
sense
all
of
the
the
hard
working it out,
problems
but
right.
I didn't understand the part with the given. With. What's the summary sentence?
The bus sentence.
The what?
The bus sentence. Like,
Yeah.
So we're starting 1.4 today?
I assume so. So that's kind of weird. Wait, didn't you go through 1.4? No, you haven't started.
If he was like a physics teacher, he would have already started going.
That's so sad. I worked so hard to get these right and I forgot the last sentence.
Amanda,
7.
Yes.
is the scan copy okay on your end?
I think so. Yeah, it looks good. All but Mason, who's gonna have to write darker.
That makes sense.
Or write in pen.
I thought you used to write in pen last year. What happened?
I just stopped.
Now that you
Calculus
need
happened.
to write in pen.
Well, I needed to write in pen then too, but
Oh, I wrote the sign backwards on one of them.
Aw.
No, I got it right earlier in the problem, but I brought it down at the final end to show my point of it backwards. This is what happens when I'm given a calculator.
So since you guys can't see the colored pen that he used, you need to check it with your original, right, Chloe?
What?
It was lower than yours.
Really?
Yeah.
Like if he makes a correction, he usually circles it, but you need to just make sure. You know what I'm saying?
Oh.
Because you can't see like the color.
But
It's
his
usually
handwriting is different than any of ours.
yes. Well, only I mean if he just like writes a negative sign, then you don't know. You see what I'm saying?
We know based on our grades. If we don't understand the material, is this class going to get worse and worse for us?
I really think derivatives are.
What?
Yeah,
You
but-
know how to do them.
They're coming.
Yeah.
What is it?
Derivatives.
Is that related to limits?
I feel like
Do you remember the average rate of change function from pre-calc? We'll start doing that soon.
Oh.
I'm worried.
It's just on a different level. Are we gonna be writing more?
He's not going to let us copy the answer key again for extra
No, I
Because if I
saw
remember
the
the
extra
things that
credit
go into
sheet,
it,
and what
I'm
you
actually
do is you
really
rework
Like
the
extra
problems.
credit?
Yeah. On all
yeah,
the
I feel like
tests.
he's
And
always
it's
on
on
gonna
my
the
get extra
exercises.
test.
credit.
I didn't lose points for
And
not
you
having.
you rework all the problems.
You
But-
read what?
You rework all the problems that you partially missed or all
So
of them
literally
missed
all of
or so all of them.
Same.
What is on the website?
It's the extra credit for the test.
Oh, he's already posted it.
Yeah. Thank goodness.
is it
Extra
rework or
credit's
is it
good.
right?
It's rework.
We only had one extra credit opportunity in Miss Claire's class,
Well, why don't you?
and that was the
already
bunny
pulled up?
question
The
that
bunny.
everyone missed.
Oh yeah.
Oh, not
Horrible
the
bunny
bunny and
question.
pots question.
Oh, the speed of the button is
I
right?
had to look that one up online. I'm not gonna lie.
And it was so easy once I showed you how to do it.
I mean,
That is
I
true.
think I was I don't know.
Yeah, it was.
But it's
I couldn't
harder-
understand why you were missing it.
It's harder to think independently.
Yeah,
We just
group
think
is
together.
No. No.
You go, Dylan.
test.
You don't want it.
Just looking at other-
Are we allowed to take these?
Do we have a lot of tests?
Oh, this is mine.
Oh.
You did better than me, buddy.
Bissing, Davidson, Carson, Arezzo, is that correct?
That's correct.
I feel like Carson will walk in
Yeah,
in the next
I'm
5 minutes.
I'm sure they'll be here, but
We do have a lot of tests in here.
Those could get 2 and 7-3. Okay, so you've gotten your test back, to you, and I guess just a couple comments. Quick one. I realize, Davidson, you can't see the red. Apparently, you can't see the red because I'm copying. That's fine, but hopefully you can follow my comments on there. One big issue I make a comment on is number 5. A significant number of students on number 5, probably a third of the students, number 5 got 0 points. Simply because what you drew was not a function. Okay, so it says sketch a function graph, and you provided for me a graph that was not a function. So there's no points involved. Otherwise, the proofs, some people did really spectacular great, others kind of really struggled with that a little bit. That's typical for a lot of practical students. So if you got it, did great. You're ahead of the curve. That's fantastic. Those are my biggest comments, I guess. Let me share this. To kind of plan for everyone, if you go to Moodle, extra credit rules right there. We're going to take a look at that for a moment. That's a lot of time. It's all written out here for you. But if you're going to earn some extra credit on your test, which you're allowed to do, you have a plan here. It's a significant amount of extra credit, so I would not turn it down if it were me. After each block test, you may earn up to 15% of the test total cost of points. By reworking questions you got wrong. So if you complete the entire sheet, you'll notice that this is not a game where you go and correct your mistakes and get half the credit back or something like that. Everyone earned 15% of the value of the test by doing the corrections. So if you read all of the rules, even if someone got every single problem correct, they can earn 15% of the value of the test. Okay. Everyone can earn the same number of points, whether 50% or 180 is. But it's 16.5, so let me check that out. So we'll have 16.5 available points, and I'll prorate that based on how many you correctly proved the work. Instructions are very precise, so we follow them very precisely. The rule is you must completely rework each problem that you got correct. And you can detail what all that means. So the rework means copy the problem and any related directions or graphs. Then rework from start to finish as if you've never even seen the problem. Don't just go in and tweak one little thing that's on your test. You got to rework the whole problem, start to finish. Problem means it includes any bonus problems. There weren't any bonus problems on this test, but if there were, you have to do bonus problems. And what do I mean by got it correct? To get incorrect means either less than full credit on the problem, which is obvious, or on a couple of your papers, you've got the word okay. What that means is, to me, I gave you full credit, but it really was kind of like, I'll let it go. But you really need to do better. So if you got an okay, you got full credit, you still got to redo that problem. Is that clear? 6. Do it on loose leaf paper. Now, a number it says here, staple the rework page on top of the original test. For the local folks at ICC, they'll have to do that. For the Davidson County folks, you're not going to want to do that because the cleaner's going to have to scan those to me. So let her collect them and scan them to me. And I already have a copy of your test that I graded and scanned back to her, so I don't need your original. I have your copy of the original already. So all I need from the Davidson folks is the rework. Make sure you put your name on each page of the rework. The number 4 on here, again, I don't know if you can see that, number 4 says, unless otherwise directed, the rework is due at the start of the next class meeting after you get your graded test back, which would be tomorrow. But I'm going to say this time, for the first time out of the gate, we're going to do it on Monday. So it's due on Monday. Rework problem is either right or wrong. You either get it 100% correct, or you don't get anything on that rework problem. And the number of extra credit points you earn will be proportional to the number that you get correct out of the number that you have to rework. That's where the real issue is. If you did very well on this test, and you don't have as much rework to do to get your points. If you didn't do as well, then you've got a lot more rework to do to get your points. But everybody can get the same number of points if they do all their rework correctly. That's number 7 is the catch-all that says if you don't follow all the directions, then no matter how much work you did, you don't get any points because it is extra credit. So, kind of an all or none type of game. Any questions on that? For anyone? Yes, Elise, right?
Yeah. How do we know what version we have?
That's a good question. Everyone had the same version on this test, so it doesn't really matter what version. Normally you would want to put, it's a good question, normally you want to put the version, like version A or version B or something on there. Everyone had the same. Other questions? Chloe?
Yeah, do you just want us to write out the problem and then our answer on like a sheet of notebook paper or something?
Yes, you want to use, one of the instructions was to use smooth edge notebook paper. So if you have it in your spiral bound notebook and you tear it out, then you got to make sure you get all the dingleberries off the side. I like this thing falling in my lap, they're a mess. Plus you can't scan them, so it needs to, especially Davidson, needs to be nice, notebook paper. Because that's something I just learned recently. I've always thought of notebook paper as being 3-hole punch, no spiral bound. I always thought of a spiral bound. Some students don't know that. Spiral bound is the notebook. The other thing is called a question, Sammy?
I don't understand number 6 on the extra credit with the whole writing perfect work the first time. Are you wanting us to rework it and put that note at the end, or just if we got something right, completely ignore it?
Number 6 says, if you earn all possible points on the original test, so meaning on this test, there was 108 points possible, and there was no bonus. If there had been a bonus, like let's say there was a 5-point bonus question, then there would have been 113 points possible. If someone had earned all 113 points on that test, then they can invoke line 6. If you didn't get every single possible point that you could have earned on this test, then line 6 doesn't apply to you. But what it says is, if you earned every single possible point, including any bonus points, then that person who did that can still earn the 15% bonus by doing the rework as directed. The rework says you must copy the problems, all this stuff, agree that you didn't get correct. But there's nothing to copy because this person got everything correct. So all they have to do is make a sheet of paper with their name on it and write across the middle of it, hey, I did perfect work the first time. I don't need to go next door. And they'll get their 15% back. Is that clarified?
Yeah.
But to me, it just isn't fair if someone does a really great job the first time, for them to not have an opportunity for bonus points. Because since this class is all based on total points, it doesn't matter where you get them from. That same person on the next test may bomb out, and they need those points to help them out. So here, everyone has an opportunity to get the same points. You never know when you're going to meet them. Is there a question?
Just out of curiosity, where does dingleberries come from? That's like
Have you not seen a dingleberry tree?
dingleberry?
Tree.
No, I haven't.
Well, neither have I, but I see them all the time on the edges of notebook paper that's pulled out of a spiral-bound notebook.
So it's like a botanical metaphor?
Yes.
Okay.
Or something.
Biological metaphor.
Go biological, you know. My dog used to have in their fur when they, you know.
Only reason.
Okay.
Your question made Sammy turn red.
I turn red all the time.
Any other questions about that?
That wasn't
What?
Yeah, that was embarrassing.
That's really gross.
Okay, well, I guess that's all the questions for now. This will be due on Monday, and I would encourage you strongly to make sure you read over this one more time. This handout on the next credit. Make sure that you are doing it correctly.
I don't believe it. You got one letter. Did you take the L or
Okay.
the W?
So we're starting block 3 at this time. Block 3 is about continuity. And we saw in this block 2, when we were looking at limits, we saw that a limit could exist even if there wasn't a point on the graph at that location. So it didn't matter what happened right at that point as long as the two sides came together. Well, that was the observation was, again, at that point it didn't really matter. We also saw the limit could not exist if the two sides didn't come together. So there was a problem there of what we call continuity. And continuity from like pre-calculus, you probably discussed a little bit about continuity pre-calculus. Usually it's you say something like this: a function is continuous if you can draw it without lifting up the pencil. So I put my pencil down somewhere and I start drawing a function, making sure you don't violate the vertical line test. And you continue to draw and never lift up your pencil, then that function would be considered to be continuous. That's a fairly loose definition, and we're going to make it more precise by using limits to define what we mean by continuity. Okay, that's what's coming up. Defining continuity more precisely by using your limits. So what I'm going to do is ask you to have your books open so we can talk and reference items in the book as we talk. And then we can look at some examples and stuff as well. So the definition of continuity is, we kind of got a couple different ways of looking at it. We start with, I guess I'll go over here this morning. a function is continuous at x equals c if
Joe, we need the camera moved up just a little bit.
Is that better?
Is that better more? More?
Perfect.
Okay, thank you. Limit x approaches c, graph of x equals f of c. Think about what that means to us, and that's a definition. So this is the first definition in section 1.4. I'm in section 1.4. Very first definition is defining what we mean by continuity at a single point. So what does it mean that the limit of x approaches c of f of x equals f of c? Can you, first of all, give me a picture, talk about a function picture, that doesn't satisfy this definition? Let's start there. What does it satisfy? A graph of the whole limit. So if I had a graph, some kind of hole in it, and that was C, then clearly this definition is not being satisfied, because f of c, even if I went in and put some point somewhere, let's say f of c was like right there, then f of c is here, but it's not equal to the limit, so it's not continuous there. How else could it not be continuous at c? To be continuous require at value x equals c, to be continuous requires that the limit value that we've been discussing for the entire previous block has to match the function value. Can you think of another picture where that's not true?
Should I try again?
What was that?
Is he talking to me?
Raise up?
Is it possible if there's a vertical asymptote at C?
Sure. Another possible graph, if this is C, might have something like this. And again, even if you were told, put a point for f of c right there, there's still clearly something not exactly right, because the limit isn't the same as the function. Good. Any other pictures that might disobey this definition, or might break this definition? One more I can think of. You got some kind of piecewise function where, that's right, Joe, where maybe you have something like that. And so here, the limit doesn't exist. So that since on this last example, the limit doesn't exist. So since the limit doesn't exist, the left side doesn't exist, and it's not going to be equal to f of c, whatever f of c is. But now notice on the red and the green examples, on both the red and the green, the limit existed. This side existed, had a value. This one was some number. This is infinity. But the limit value is not the same as the f of c. So all of those are examples of being discontinuous at c. So now if you take out all of those, then whatever's left is continuous. In fact, these three cases have specific names. This first case in red is called a removable discontinuity. I mean, in some sense, all of them are removable if you really want to argue it. But this one has the name removable discontinuity because it would be fairly simple to eliminate the discontinuity by simply putting your finger on this point and just sliding it up the graph and putting it in there. So now it's removable. We call that removable. Others, again, are arguably removable, but not in the same fashion. The green graph is said to have an infinite discontinuity. I think it should be fairly obvious why that has an infinite discontinuity. Is it obvious to you why that has an infinite discontinuity?
Because it's not continuous and it goes to infinity?
Yes, because it has a vertical asymptote, and it could either, infinite discontinuity could have both sides going to positive infinity, which we would say the limit is infinity, or it could be both sides went to opposite direct infinities and still be a vertical asymptote and still be infinite discontinuity. And then the third case up here, the one in purple, which I don't know if you can make that out as different from black on the video camera, but this third case here, we call it a jump. So those are the three kinds of discontinuities. Otherwise, it's continuous. As long as those things aren't happening, then we say it's continuous at C.
The color that you wrote the function in, the cameras having a really hard time picking that up. Was that black or?
That was black.
Can we not use that color?
Are y'all seeing this?
Yeah.
Are you seeing this?
Can you see that?
Yes.
Okay.
Is that black?
See, our feed,
Our feed doesn't show it at
our
all.
self feed doesn't look as good. I'll shut this door. That may help too.
Okay, with the light, yeah.
Oh. Wait, so is that purple or black on the left? Yeah, that's what I thought.
Okay. So, in order to show something is continuous at a point, then you have to show that it is, the limit is the same as f of c. Now, how did we discuss the limit before? Let's kind of delve into this aspect right here. If I was going to try to show that, what do I have to do with that? Like on your last test, how did you show something about the limit x approaches c of f of x? I looked at from the left side and the right side. Remember that? So, so this would require that the limit x approaches c from the left side of f of x has to equal the same number, so some kind of value L, and that has to equal the same number as the limit x approaches c from the right of the function f. So we had kind of two sides to that idea. And then this f of c, so now we're saying this, all of this has to be equal. So since the two sides have to be the number L, and what this is saying to me is, if you bring this part into the picture, that says f of c has to also equal L. You just have to show all of this in order to show it's continuous at a particular point. Okay. Well, let's see what else we got in the book. I'm going to wander back over here to my book for a minute. On the next definition on page 109, they actually define what I just talked about there, the left and right continuous. So left continuous, that's general. What we just talked about was general continuity. Remember, at left limit and right limit, and I used a general limit over there. So left continuity is going to require just left side, and right continuity is going to require just the right side. So left continuous at x equals c. You have the limit x approaches c from the left of f of x has to equal f of c. Notice that technically this is part of the general definition, but it's allowing me, I can talk about, for example, well, this one's not left. Right continuous is similar, and we'll make sure tie it back over here to this picture. So right continuous at x equals c means same type of thing. The limit when x goes to c from the right of the function f of x is equal to f of c. So these are just special kinds of continuity where we're allowing only one-sided continuity. But we still have to have the function value equal to the one-sided limit in order for one of these to exist. So back over here on these three pictures, I'll pan back over these three pictures here. So this removable discontinuity was discontinuous at x equals c, but it was also not left continuous. Left continuous would mean that I have to come in from the left side, and the left limit has to be the same as the function value. It's also not right continuous because I have to come in from the right side and hit the same function value. The infinite discontinuity is not left nor right continuous because the limit value from the left or from the right doesn't match the function value. But on the jump discontinuity, notice on this particular jump picture I made, the left side is left side not continuous because the left limit doesn't match the function value, but it is right side continuous because the right side limit matches the function value. Are we following that thinking there? This picture here is right side continuous at C. It is not left side. Are you clear on that? Yes, no? One more time.
I'll take it.
Left side, right side just have to do with which side you're looking at and whether the point is included in that limit or not. Seems kind of obvious. Now, a broader picture is continuity on an interval on page 110. I'm not going to try to write this one down for you. It's a fairly long definition. But let's read through it and then talk about it. So page 110, definition 1.14. Continuity of a function on an interval. So not just at a single point like we've been talking about. Now we're talking about a whole interval of points. A function f is continuous on an interval I if it is continuous at every single point in the interior of I, and it is right continuous at any closed left endpoint, and or it is left continuous at any closed right endpoint. Well, that's a lot. Well, let's look at this. Look at the four pictures down there right below it to see if this makes sense. The first picture, the book says is continuous on the interval 1 to 3, open on both ends. We see that that's true. The endpoints are not included, so it could not be either left or right continuous. Now, look at the second picture. The left endpoint is included, so you would say that this is right continuous at x equals 1. See that? X equals 1's on the left side of the interval. But you would do a right-handed limit to come into x equals 1. So at x equals 1, we say it is right side continuous. Every point in between the endpoints is continuous. And the right-hand endpoint is not left continuous, not equal to the function value. Therefore, it is continuous on the closed interval 1, but open 3. The next one is continuous on the right side, so we would say that it is left continuous at x equals 3. Left continuous at x equals 3. Again, even though 3 is on the right-hand endpoint, you're approaching 3 from within the interval from the left-hand side. So we say that it is left continuous at x equals 3. It's continuous at every interior point. So it's continuous on 1 to 3. And 3 including 1 not. And then completely closed interval 1, 3 requires left continuous at x equals 3 and right continuous at x equals 1, which it is in fact. And then we have to see the distinction of those 4 cases. Okay? And just keeping clear again, even if it's like seems backward, but your left-hand endpoint needs a right continuous, and your right-hand endpoint needs a left continuous. We've already discussed types of discontinuities right here. On page 111 at the top, they kind of define that a little bit better. We talked about it graphically. There's definitions right there on page 111. Let's see if that makes sense from what we just drew and discussed. See if these definitions make sense. Removable discontinuity if the limit of f of x when x approaches c exists, but is not equal to f of c. Does that match what we see on the removable discontinuity again? The limit exists, but it's not equal to f of c. And jump discontinuity occurs if the limit of f of x as x approaches c from the left and approaches c from the right both exist, but are not equal. So then we have a jump discontinuity, and the left and right side limits exist, but they're not the same number. And the infinite discontinuity is defined more precisely by if one or both of the limits as x approaches c from the left or the right is infinite or negative. So if one or both are infinite, and you could have, so if only one of them was infinite, could you draw a picture of that? Back over here, could you draw an infinite discontinuity with only one side being infinite? It says either one or both being infinite. Now, I have both sides infinite here. So this is an example of infinite discontinuity with both sides being infinite. Are we clear on that? I'm asking you the question. The definition says at least one has to be infinite, not necessarily both. So can you draw a picture with an infinite discontinuity where not both of them are infinite? Not both sides. That's the question. The ideas. First, we need an asymptote at C. I'll agree with that. Okay, so something going on here that's not an asymptote. So I'm going to need like an open circle right there. Now, do I have to have an open circle there? Well, I could define a point right there if I wanted. And or open circle either one. And that would, yes, that would now be considered, it's sort of a hybrid. This is sort of a hybrid of a jump and the standard infinite, but we'll call this one an infinite discontinuity rather than a jump discontinuity. Okay. So far, so good. let's see if we can do an example. What we might be talking about. Okay, so let's look at an example of how they title files. Here, look on page 115 with me. This is a curious example number 2 here. This example 2 on page 115 is kind of a little maybe beyond our scope in terms of trying to prove anything with this, but we can certainly discuss it. And the functions given, like function A, is a piecewise defined function where it says f of x equals 1 if x is rational, and it's equal to -1 if x is irrational. And the graph below on the left-hand side is a graph of it. There's 2 different dotted lines. The one with the bigger dots is the one for where x is rational, and the one with the smaller dots is the one that's for x is irrational. Now, first of all, you'll understand that is actually a function. You're like, well, it doesn't pass the vertical line test, right? It looks like 2 lines above each other, and you would say, well, what about the vertical line test? You just gave me 0 points because I drew a graph that wasn't a function. My question is this a function picture, or does it fail the vertical line test?
Dang.
Exactly. It is definitely a function because if x is rational, it has one output, number 1. And if x is rational, then it cannot be irrational, so it won't have a point at -1 below it. Clear? So it is in fact a function. It is everywhere discontinuous. I mean, you got holes everywhere. You have infinite holes everywhere. But we're asked to look at the limit as x goes to 0. So we're talking about continuity at x equals 0 at a particular point. So we're asking about the continuity at x equals 0 in this picture. What do you observe? As you get close to x equals 0 from the 2 sides, what do you observe? It just jumps back and forth, doesn't it, like this?
Yeah.
So the limit doesn't exist on either side because you're kind of like just jumping back and forth. Sometimes you're at 1, sometimes you're at -1. Just jumping back and forth. And so the limit doesn't really exist coming towards 0. It sort of feels like it's going to go to 1 on the upper line. It feels like it's going to go to -1 on the lower line, but it really doesn't, because imagine putting, like on the upper line, let's say you're coming from right. If you put a narrow band epsilon around y equals 1, can you find a delta so that all of the values in that delta are in that epsilon? No, because there's always going to be infinite of them that are down here because you got irrationals between every rational. So that's obvious. But now what about the second picture? The function is similar. G of x is equal to 1 if x is rational. And g of x is equal to x plus 1 if x is irrational. So picture now is let's see color. So it's equal to 1 if x is rational. So this is x is rational picture, and then you got x plus 1 if it's irrational, which is going to be so this is x is irrational. So again, x values, as you're running along the x-axis, you're hitting between any two rational numbers, you're hitting infinite other rational numbers, and you're hitting infinite irrational numbers between any two rational numbers you want to pick. But as x goes to 0 on this picture, what do you observe? As you're coming in towards 0, you're bouncing all up and down all over the place here. But as you get closer to 0, what happens? The bouncing gets smaller and smaller, doesn't it? So the idea is, once again, going back to what we've just done, if you were to draw in any epsilon window here, so this is 1 plus epsilon, this is 1 minus epsilon, then you should be able to find a delta range so that all of the output values are inside the epsilon window. And therefore, the limit from left and right goes to 1. Okay? Let's make sure we're clear. So, limit x approaches 0 of f of x, I guess it's called g of x. G of x. G of x is equal to 1. Why is the limit as x approaches 0 equal to 1? Because I can squeeze, no matter how small I make my epsilon window, I can squeeze a delta to get all of the outputs in that window. Absolutely. So this is true. What is g of 0 equal to?
1.
How do you know it's equal to 1?
Because that's the limit.
I mean, you could graphically put it in.
I can also use the, go ahead. Finish your statement.
Is 0 a rational number?
0 is a rational number. So since it's rational, and the output is 1. Since these two things are the same, since those two things are the same by definition, this function picture is continuous at x equals 0. That's an odd concept, because once again, I've got two dotted lines here that have infinite holes in each line. But at x equals 0, by definition, it's continuous. Okay. Wild, isn't it? That's just kind of cool. Now, we have a very important, very powerful theorem called continuity of very basic functions theorem, or on page 111, theorem 1.16. Continuity of simple functions. Write these down. So, that x approaches c on mx plus b, lc plus b. That's basically what it says. And, well, that's part A. Part A has 3 parts to it. I'm going to skip the first 2 because, to me, they're incorporated in the third part. The third part of Part A, third statement of Part A, is a broader statement of the first 2 parts of Part A. And then Part B says, limit x approaches c of the function ax to the k is equal to a times c. What in the world is that? Why is that important to me?
Why?
By the way, we're gonna prove the first part, first one, in just a moment, because you now have done a lot of proofs of limits. How do you prove limits?
Math, algebra. I mean,
Using
yeah, you
what?
you connect the epsilon and the delta windows.
Correct. We do the proof. Let epsilon be greater than 0, choose delta, blah, blah, blah. We'll do that in just a moment. The second one is a little more complicated, so we'll let that one go. It really would involve factoring of the difference of two n powers. You know how to factor the difference of squares. You may remember how to factor the difference of cubes, but in general, there's a generalization of that, factoring the difference of two n powers. We won't get into that. We won't have time for that. So, but why, before we try to prove the first one, why is it important? What does it say to you?
Why is it important? Why?
Yeah, basically, exactly. If you view this as f of x, then what is the right-hand side of this statement equal to?
F of C.
That's simply f of c. That's right. So
That makes sense. Because it says x approaches C. Yeah. Got him.
So this is saying the limit of this function as x approaches c, left side of my definition, is equal to f of c, right side of the definition. Which means that this function is continuous across its entire domain. It doesn't specify what c value it is. C can be anything.
It's C.
It doesn't even specify what m or b are. It can be anything. And you will be able to find the limit without having to take out a calculator, without having to use a table, like you did on the last test. We used a table and you said, oh, look, the limit's getting close to some number. Well, now on this function, we can say what the limit value is going to be fairly quickly, because this is effectively saying, all of this is saying to you, this theorem, in general, is stating f of x equals mx plus b is continuous at all x equals c values. So that it says a lot. It's like, it doesn't really say it, but yet it does say it. Okay, and then the same thing down here, this type of function, this is f of x, and if you plug c into that f of x, you get f of c. So this statement is saying the same thing for a different kind of function. So f of x equals a times x to the k is continuous at all x equals c values. The first function is, of course, known from pre-calculus as a linear function. We recognize that immediately, do we not? So this is linear, and this one's called power.
Power. Oh.
Power. Is power if the variable's in the base and the exponent is fixed. It's exponential if those roles are reversed. So this is called a power function. We'll look at others later. These are the only two that are specified in this section. Let's now take a moment to actually prove this first one, and we'll just agree that the book is right, that this is in fact true. Again, it can be proven, but it's a little more in depth than what you get into. So I'm going to go back over to the left forward now, start over. So we're going to prove that. And I want y'all to, I seriously want y'all to not just be copying. I want you to tell me what we need to write in order to prove this. So once again, I'm going to write down what I'm supposed to prove. So I've got it right here in front of my eyes. Make sure that's what we're trying to prove. So high enough. prove that the limit x approaches c of mx plus b is equal to m times c plus b. So that's what we're trying to prove. Now that should look just like on your test, the very first proof, I think, was problem number 7. If you look at your test real quickly, you'll see limit x approaches, read it to me. Joe, you got it. How else will? Limit x approaches.
Limit x approaches 3 of 2x minus 7 equals -1.
So that's what you had to prove. And we're just saying, here's where that -1 comes from. Okay, now we're going to do it in general for M and B and C unspecified. Everything's unspecified. Do it. How do we start the proof? Help me out. How do we start the proof?
Well, given given epsilon is greater than 0.
Or yes, either way. Given epsilon greater than 0, given any epsilon greater than 0, sure. Then what? Choose what?
Delta equals blank space.
We'll leave it blank space. I'll go with that for a moment. We'll do that. Absolutely. That's exactly how we set it up before.
Yeah.
Then what's the next step?
Assuming x
Some x located such that.
That depends on what
Where do
you
we want
want.
x located?
You want the absolute value or the thing with like the is an element of sign? With the euro sign.
Is less than the absolute
X
value.
minus
You know the
C.
euro sign? Oh, they
X
want
minus
that.
C is less than delta.
Good. Who was that? I heard Razor before. Who was that this time? Thank you, Britt. Keep going. Good. Thanks, Jacob.
Say this, James. Just get it.
Okay. Let's see.
Do you want to use scratchwork or you want?
We're trying to get to the conclusion. Remember the definition had for any epsilon there exists a delta where if this is true, then something happens. So we're to the then part. What do we want to happen? Absolute value, yes. Of this function, mx plus b minus plus b, limit value. We want that eventually to be less than epsilon. That's exactly right. Y'all are on this now. Good. So how do we go from here? Doing good so far. That's exactly the plan. Where do we go from here?
Can you do b minus b?
Yeah, I'd say let's do a little cleanup of our algebra there. That's a good idea. So looks to me like b's just kind of go away, and I can factor an m, so I'd have an m times x minus c, like that. I follow that little bit of algebra.
Yeah.
So absolute value of m times absolute value of x minus c.
Oh my gosh, that's awesome.
So wouldn't that be less than delta?
Which is, and I'm just going to wrap around here, equals absolute value, excuse me, not equals, less than absolute value of m times delta. How do I know it's, how do I can put less than m, absolute value of m times delta? What tells me that?
You're assume.
I already said x minus c absolute value is less than delta right there. So I just substitute x minus c absolute value with a less than delta in here. My objective, one more time, is to do what? Get it what?
To epsilon.
Less than epsilon. So I need to get less than epsilon right here. That means I'm allowed to choose my delta. That's the one piece of the puzzle we left blank. You get to pick. What do you want your delta to be equal to so that you get an epsilon at the puzzle?
Make it 0.
Make it epsilon over m.
Why?
Because then the m's cancel out. You
Well, he
just
said
have
it could
to
be
On
anything.
over, be careful, not over M. You're almost right.
Oh, yeah.
Yes, absolute value of M. Good. Because the point was, M could be negative, but your delta needs to always be positive. Must be positive. So epsilon is positive. So if M would happen to be negative, then you would get a negative delta. We don't want that. So this is equal to absolute value of M times epsilon over absolute value of M. And
Hang on a second. Hang on.
Question? Question?
I'll take it.
You follow it?
I'll take it.
Okay, so we've shown that this is true. And since that's true, then it means it's continuous at all C values. Okay, we all follow that? That was a good review of our proof, so we just skipped it.
I thought I was done with proofs, but I was sort of mistaken. I'm just to prove myself for the rest of my life. It's just a metaphor for my life. I have to prove everything. Nothing's given anymore.
Oh, that's good if you're trying to prove everything. Substantiates what you believe rather than just believe.
Yeah, that's fair.
Second part, like I said, is also true. It involves a factoring that I don't want to spend time getting into. It's not that big a deal, but it's kind of beyond our scope. So we'll just accept this is true. So meaning, if I want to find the limit, of a power function, I can do so fairly simply by simply evaluating the power function at the limiting x value. Fairly simple. Okay. I don't think I need to go a whole lot more with that. Five. Real quickly, we need to cover the last couple of theorems here. I'm on page 113 now. Page 113.
Extreme.
Yes. We have two theorems that kind of look at two different aspects of functions. The first one is called the extreme value theorem. And the second one is called the intermediate value theorem. So they're dealing with, like we've talked about, in behavior, and did you hear those terms in pre-calculus? In behavior of a function, and then where do you have maximums and minimums? Well, that's kind of what this is getting at here. So the extreme value theorem is saying that if the function again, reading through the theorem carefully, remember all of the hypotheses have to be satisfied in order to draw the conclusion. If you leave out any of the hypotheses, you may still be able to find an example that satisfies the conclusion, but you're not guaranteed. So let's look at the theorem 1.17 and read it carefully. It says if f is a continuous function on the closed interval a to b. So you got in your mind what that means? Continuous on closed interval a to b. Don't pick up your pencil when you draw it, and the endpoints are included. Okay? Then there exist values capital M and lower m in the interval a to b such that f of capital M is the maximum value of the function on the interval a to b, and f of little m is the minimum value of f of x on the interval a to b. So again, one more time, if you are drawing a picture without lifting your pencil, you've got an interval from A to B. Let's say there's f of A, and it's included, and there's f of B. Draw a picture from there. Okay, so whatever you draw, you can't pick up your pencil. So whatever you draw, I drew it without picking up a pencil. You see that there's got to exist some value in here, some x value, so that we achieve a maximum. What would that x value be? That looks like m because f of m is my maximum. Capital M. Where would my minimum be located on this one? Now, little m looks like it's going to be there because f of little m is right there. Does it say that the maximum and or minimum are unique, meaning there's only one place that it happens? Or does it say, what does it say? There exists. What does the word there exist mean? At least one. At least one. Not only one, but at least one. So you could have more than one capital M, and you could have more than one lowercase m. Are we clear on that?
That's cool.
Next theorem real quickly. The intermediate value theorem. Again, fairly obvious, but it's a little deeper than you might first think at first glance. If f is continuous on the closed interval a to b, so same starting hypothesis. Don't pick up a pencil, include the endpoints. So you've got some function like that. Then, for any k value that is strictly between f of a and f of b, there exists at least one c value element of a open interval a to b, such that f of c is equal to k. Well, let's just use this picture right here. Okay, so on my picture, this is f of a, and right about there is f of b. We all agree that this is f of a and there's f of b on my picture approximately. Okay, I'm going to pick a k value between those two numbers. There's a k value right there. I don't, again, purple doesn't show up different, but let's deal with it. There's a k value. Do you see k value between f of a and f of b? And it says strictly between. So I'm not at f of b and I'm not at f of a. Strictly between. This theorem says that I've got to be able to find at least one c value. So there's a c value. There's another c value. Maybe even there's another c value. So that f of c equals k. Seems obvious to me. Another way to think of that is, can you always go faster than your average speed when you're driving?
Yeah.
Can you always go slower than your average speed? So that idea relates to that. I'm not going to get into it much more, but kind of relates to it. And then the last theorem, real quickly, and I know we got to go, is on page 114, and it's just a special, kind of a special application of that theorem. So the intermediate value theorem says that you can always find a location to hit a value that's intermediate between. Intermediate means between. So if I have a value between, I can always hit it somewhere in there. The last theorem says this is how you determine about sign changes of your function. Sign changes on a function, what do we mean by that? It goes from plus to minus or minus to plus. The only time a sign change can occur is that if the function crosses the axis, which is done in pre-calculus, but also when it's discontinuous. When you have a discontinuity, you can switch, or if it's undefined, of course, like if you have an asymptote. So the sign can change not only at crossing the axis with an intercept, but also at discontinuities. And that is simply applying the intermediate value theorem. And how is it special case? How do I apply the intermediate value theorem for the idea of sign change? Well, sign changes, that means you're going from plus to minus or minus to plus. So what special K value am I considering on that last theorem? If I'm changing signs from plus to minus or minus to plus, what special K value might I be considering in my intermediate value theorem? K equals 0. That's exactly right. So that theorem is, to me, just, it's like a lemma. It's a special application of that intermediate value. Okay, so you got homework already posted on Moodle for section 1.4. And see you tomorrow.
Yeah.
Last time we got out early. This time we got out 2 minutes late. So I'm hanging out maybe later.
Miss Klinger, do you like special K? Like, yeah.
Why is it so?
Really? Dude, I got one that has like these chocolate chunks in it.
Oh, the
Oh my gosh, those are freaking awesome.
It's great. Cereal. Oh, crap.
Yeah, bro. Special K reminded me of my ex.
It was good, but when I was
Yeah. Wait, so did you take the L or the W? How big is the L? Small L?
pretty big.
Oh, okay.
14, right?
What was 14?
No, not 14.
What was the one you got?
10. The one that was worth 14 points. That's
Oh,
just
the quiz?
function graph.
Yeah.
I thought that meant a graph of
I mean,
functions.
Oh.
grades are really weird. He was talking about how
Number
grades like you would grade in a few years.
Look what I drew.
You should talk to Brittany.
Like, I would.
Look what I drew.
Hey, Brittany, Chloe needs help with number 5. I do. I don't know what I'm doing. You got this?
Yeah.
All right. Show me how it's done.
Look at how simple it is. Oh my gosh. Got him. I think I like math.